Hello, everyone. We're Group 26, and today we're going to talk about the implementation for assignment 2. My name is Chris, and here is Joost, this is Xue, and this is Mart. So, for our implementation, we try to make our solution both smart, quick, and frugal. So, the approach that we have taken to implement this project is by um, assigning each member to one of the strategies. So everyone had their own branch and everyone just worked on their own branch until they were done. And then we tried to merge them onto the master branch. So since we worked on all the strategies, we're going to talk about all the strategies one by one. So I talk about how we came to the idea, and then we'll talk about the solution that we've actually implemented. So we're going to start off with the SMART strategy. So for the SMART, we were supposed to find a better query evaluation plan. And in the original code, the simple evaluator basically evaluated the AST, the query AST from bottom to top. And instead for this, we thought of the following solution. So in the preparation phase, we first calculate and then list all the cardinalities of all label edges, like this So when our solution actually gets the query, we first examine all the labels, and then we look at the label that has the lowest cardinality. So we can give an example. So let's say we have a path 1, 2, 3, 4, and we say 2 has the lowest cardinality, then we pick 2. So we've picked the edge label with the lowest cardinality. So after that, we retrieve all the triples that are associated with this label. And then the next step is to look at the edge label left and right from 2, let's say, from our example. So which are 1 and 3. And then we look at their respective cardinality, and then we pick the lowest. And then what we do is we join those two together. So let's say 1 has the lowest cardinality, then we pick 1, we retrieve all the triples, and then we join 2 and 1 together. And then basically what we do is we repeat this algorithm until the whole query is evaluated. And our solution should be faster because we lower the sizes of the intermediate joints. And we have seen a score reduction of around 300 as a consequence of this solution. However, when we try to merge this method with all the other methods that we've created, it did not yield any significant results. So now we move on to the quick strategy. And for the quick strategy, we were supposed to find a better way for the physical evaluation of the query plan. And we have implemented a total of 3 methods. So the first improvement we've made is, again, in the preparation phase. So recall that in the original code, the program loads the whole full graph from graph nt into a data structure. And then whenever a query is executed, it needs to look into this data structure, this full graph. So this is obviously not efficient because there are certain things we know about the query and we can narrow it down, let's say. So an obvious improvement for us is to divide the larger graph into smaller graphs, let's say. And then we divide them based on their edge label. So we'll have one graph only for triples with edge label 1, one for only edge label 2, and so forth. So why do we bother with this? Well, the biggest advantage to this is that we do not have to evaluate these queries anymore. And then we're talking about the singular queries, like a single, like a 1, and then with the arrow forward or the arrow backwards. And instead, we can just retrieve them instantly. And the second improvement we've implemented for the quick strategy involves caching. So whenever we perform a join or a plus query, we cache its result and every intermediate result. So this brings obvious benefits. For example, same queries that we have evaluated already do not have to be re-evaluated anymore when we encounter them. So, but instead we can just retrieve this from memory. So just with these 2 strategies that I've just mentioned, we were able to bring down the score by around 850 points. So the third improvement we've made for the quick strategy is an join function. the join function joins two graphs, right? Left and right. So the original code, what it does for joining is that it looks through all the triples on the left graph, and then it reads the target on the left graph, and then it finds the corresponding right graph. So essentially what's happening is that for every triple in the left graph, we'll need to find the corresponding triples in the right graph. And this is obviously not efficient because we would need to load the triples constantly into the into memory. So in order to improve this, we have tried to sort the left and the right graph on their joining attributes. So that we can minimize the amount of IOs that are being done. This method is largely inspired by the merge join algorithm from the lectures, but since the given data structure is different, we do not actually sort on the joining attribute. So instead, what we did was we picked the left graph and then we turn it around. So we picked the reverse graph and then we join them on the target from the left graph with the source in the right graph. Although this is a pretty easy solution, right? Just taking the reverse of the left graph and then joining them. But we were still able to get a pretty significant score reduction by around 300 points. But this could only be achieved in isolation because once we would try to merge our solutions together, it only generated around a score reduction of 50. But this is probably because we were just doing fewer joins in general. Because recall that in the second improvement that we've made, we do more caching. So we can just look up easy queries that already have been done instead of just redoing them. So that probably might explain why the score reduction is not as significant. And now for the last strategy, the frugal strategy. For the frugal strategy, we were asked to be more memory efficient, right? Especially with respect to the graph data structure. And in the original solution, the triples were stored like this. And the problem with this is that the vertices with no edges still take up a lot of unnecessary space. And we have tried multiple solutions to improve this, but unfortunately, we weren't able to find anything. So some of the solutions that we've tried are a sparse matrix or just changing the formatting of the original data structure. So while we were able to bring down the memory usage, we were, however, not able to make it any faster. So most of our solutions were unfortunately slower than the original solution that was provided. So as a consequence, we were not able to bring down the score at all either. So this brings us to the last point that I want to discuss, the further improvements. So since we're not able to find a good method for the frugal strategy, the coming few weeks we will be doing our best to find a good method for this. We're gonna try to find a good method that is one memory efficient, but also fast enough, or at least faster than the original code. So this concludes our video, and I hope you had a great time watching my video.